Here's your clicker.
Thank you very much, Steve. OK, so I've been asked to talk about biosignatures and technosignatures as complementary paths to life detection. And in particular, how we really should be pursuing both as sort of a mixed strategy. And the truth is that they have sort of evolved in parallel, but they've had very different fates since they were first seriously contemplated by modern science. So we want to talk about some early life detection experiments. We can go back to Project Ozma, which started around 1960 when Frank Drake, as we just heard, started looking for the sorts of signs of technology that Earth at that time was already emitting, essentially looking for technological life like our own. And then in 1976, perhaps the first serious life detection experiment for microbes that had a good chance of success, the Viking-labeled release experiment, where the Viking probe took some Martian soil, exposed it to some nutrients and warmed it up and looked for signs of metabolism. And so here we're really on opposite sides of the spectrum of what we could be looking for. With the microbes, we're looking for a very generic sort of molecular level evidence of life, presumably from microbes, that you wouldn't even be able to see if you were holding it, all the way to radiotechnology, which in some ways is the most sophisticated and contingent sign of life that we might find. So I've often heard it argued that obviously we should be looking for the microbes instead of the radio waves. And the two, if we could go back one slide, I don't think I have that button. These two efforts have been, oh, here we go, sort of in parallel. And this one on the right, NASA has been pursuing with ever more vigor. And now we have NASA Astrobiology Institutes. We have astrobiology as a major field of study that you can get a PhD in. And what I think are some very sophisticated methods for going about that, fully supported by NASA. On the left, looking for technosignatures. For a while, NASA was interested, and then in the 80s and 90s, notoriously, it was cut from the federal budget. And for many decades, basically had to move to the philanthropic side. And so the two methods have been pursued in parallel, mostly by different people, and without a lot of cross-communication between them, despite the fact that they're actually quite similar in a lot of ways. And I've heard people on the astrobiology side, the searching for microbe side, claim that it's obviously the better way to do things, that by necessity, by simple logic, it must be easier to find life, microbial life in the universe than technological life. And so I want to walk through what I think that argument is and why I think actually both methods are perhaps equally likely to generate success. So I think the argument that microbes have to be a better bet goes back, ironically enough, to the Drake equation, which Steve has introduced us to. So the first parts of the Drake equation, the first few elements of the Drake equation, describe the mean number of sites for complex life in the universe. So we could write down a Drake equation for biosignatures in the galaxy, and it might look like this. All I've done is I've trimmed the equation. I've changed L to the lifetime of detectable biosignatures, and I've captured everything else. I've just folded it up into a single F. I've just trimmed out everything that doesn't involve technology. I can then do something very similar for technology, where now I have the lifetime of technosignatures, and I've combined the fraction of planets with intelligence times the fraction that develop technology into a single FT. So all I've done is in the previous one, I've changed it to biology and kept FT out. And in this one, I've just combined FI and FC. And if you put these together, we can ask, how many more sites of biology are there than sites of technology? And if you take that ratio, you get this, and it looks like it should be much less than 1. So all I've done is sort of capture this intuition. It says that the fraction of planets with technology must, by definition, be less than the number with some kind of life on it, because technology is not inevitable. So this number must be less than 1. And then we think about the lifetime of biology on Earth, 4.5 billion years or something. We think about the lifetime of technology on Earth, perhaps centuries. This number is much less than 1. And so obviously biology is a better bet. So it seems like the Drake equation itself argues against SETI, but this is not correct. So there's a few flaws in the argument, and these flaws in this argument go back to the 1960s. This is nothing new. I'd like to point out in the solar system that as far as we can tell, the number of sites of biosignatures is 1. There may be biosignatures elsewhere in the solar system, but we're right here and we haven't found them yet. So if they're there, they're pretty subtle. On the other hand, the number of sites of technology in the solar system is at least 4. There are at least 4 planets in the solar system where we regularly detect radio signals from our interplanetary probes. And if someone were looking from afar, they would see 4 planets that have technosignatures and 1 with biosignatures. So I think this illustrates the first fallacy, which is, oh, and these are very weak technosignatures to be sure. Mars doesn't have many radio waves, but there's really no limit on, in the future, we might have many more. So this point that technology can spread is an important one. So Manas V. Lingam in a work in preparation describes so-called service worlds. These are worlds where there is technology but no biosphere. These are worlds where technology has spread to. If in the future, distant future perhaps, we have colonies all over Mars and lots of technosignatures there, that is a perhaps precondition to terraforming Mars and bringing a real biosphere. It's very easy to imagine that in the future, Mars has a long period with many technosignatures but no biosignatures. And because there's no biosphere, there's no limit on the technology. Here, if we were to cover the planet with solar panels, that would be very bad for everything on Earth other than the solar panels. But if we were to cover Mars with solar panels, the geologists might not like not being able to get to the rocks, but there's no negative feedback on a biosphere. And so that particular limit on how big technology can be is only relevant to planets with biospheres. It's not relevant to all the other planets. Technosignatures on service worlds, therefore, could be much stronger. You could have much bigger technology, much louder technology, much more obvious technology than we have here on Earth today. Now, life can also spread even beyond nearby planets. And this is a very old argument that the galaxy, once a technological species starts spreading among the stars, will lead to exponential growth. So just to illustrate the point, let's make some conservative assumptions. We're not going to go Star Trek with warp drives. We're not going to assume that we don't understand laws of physics that allow us to populate the galaxy. We're going to stick to chemical rockets. Let's just say it's very rare. Now and then, a technological species manages to settle a nearby star, and it happens every 100,000 years at most. Let's further say you can only go to the very nearest stars. We're not crossing the galaxy. We're waiting for something within about 3 parsecs. So there's a handful of stars within 3 parsecs. One of them might have a place worth going to, and that's all you get. So what we're talking about, if we go at sort of chemical rocket speeds at 10 kilometers a second, is a 300,000-year journey. That's hard. I don't know how to do that. But that's not impossible. There's nothing that's just engineering, if you like. And after all, you only have to do it every 100,000 years. If you want to go much faster with other kinds of propellant, that's fine. Maybe you can do it in 300 years. I don't care. It doesn't matter for this simulation. We then ran a simulation, which I hope we can get on the monitors because the contrast might show up here, showing what would happen with that scenario. So in this simulation, done by Jonathan Carroll Nellenbach, a single point in the galaxy, this is the galaxy, begins to have life that spreads to other nearby stars. And again, this is very slow. The little purple points you should see in the monitors slowly growing are the number of sites where this has developed. And it takes a long time because their probe length is very small. And over the course of a few 100 million years, things start to take off. And when you start to get to places of higher density of stars, then you can reach that maximum of a trip every 100,000 years per star. And what happens is exponential growth in the center of the galaxy, and pretty soon, technology is everywhere. So this is an old argument. It's a naive argument. But the point is that I've put in very conservative parameters, and so it's robust. The galaxy, many have argued, should be filled with technological life if it spreads among the stars at all, even with conservative assumptions. So it's not warp drive science fiction. So this is actually in tension with the Drake equation. I don't think this is often appreciated, that the Fermi paradox and the Drake equation have almost antithetical assumptions behind them. The Fermi paradox, where is everybody, assumes that if life exists, it will spread to every corner of the galaxy. That's the question. Why hasn't it? It should have done that. And the Drake equation implicitly says it stays put, because it says that the only place you find technology is a small fraction of the planets with biology. This is not a criticism of the Drake equation. The Drake equation serves many functions, but in this particular way, it's somewhat misleading. So I would personally guess the answer is somewhere in between. I don't think galaxy doesn't seem to be filled with technology around every star, although it would be hard to know, frankly, so I don't know that. But I also think it's likely that life does spread among the stars to some degree. So what does that mean for our equation? Well, this number here, the fraction of planets with life that get technology, could be much more than 1. In the solar system, it's already 4. So we should not assume that this number is less than 1, and if you believe the logic of the Fermi paradox, it could be as large as the number of planets in the galaxy. The second flaw in the argument has to do with the L term, the notorious L term in the Drake equation. The fact that Li, I should say LT, the lifetime of technology is less than the lifetime of biosignatures is only true in Earth's past. We don't know what it will be for Earth's future. And so we don't know what the actual value is elsewhere. It's very natural to say we're comparing centuries to billions of years, but we don't know that. Humanity is the first species that can prevent its own extinction. And so many of the things that brought an end to other species may not apply, especially asteroids and things like that. So right away, we've got a longer potential future than other species. L is also often linked to things like nuclear war, or the collapse of civilization, or catastrophic climate change. But the truth is, those won't lower L, unless humanity goes extinct. On a cosmic time scale, a little thing like a collapse like a civilization doesn't matter. We still are around, we can still grow again, and we still have technology. It's only human extinction that ends L. And that is a much rarer event than all of the foreseeable catastrophes that we are rightly worried about. There's another problem too. We have other intelligent tool-using species on Earth. We're not the only ones. We're the only ones that currently have the sorts of technology we see, but evolution works, and if it happened once, there's no reason to think it might not happen again. And anthropologists are quick to remind me, it's not clear what is so special about humans that have allowed us to do this with technology. There's no single trait humans have that is unique to the animal world. It's the constellation that seems to be important. So even if we were to go to extinct, maybe a super plague or something like that, other species could still try again. We've still got hundreds of millions of years left in the sun's lifetime where technology could arise again. And even if we are especially self-destructive, we should not assume all technological species elsewhere are similarly self-destructive. So regardless, it's not at all obvious that the lifetime of technology could not be similar to the lifetime of biosignatures. And I'll go even farther than that. Technology can persist beyond the destruction of the biosphere. If we really are going interplanetary, if we really are going interstellar, then the end of the sun's main sequence lifetime is no obstacle. So if technology still exists on Earth in 1 billion years, the Earth's biosphere will be gone. It'll have boiled away. But there's no reason the technology couldn't have moved to Mars or beyond. So in fact, it's reasonable to hypothesize that technology can outlive biology by many factors. So it's not at all obvious that that last term in the Drake equation, that ratio, needs to be much less than 1. In fact, it could be greater than 1. It's a long tail in the probability distribution out to large numbers. So let's look at another point on the scorecard. Let's look at the ambiguity. Many technosignatures are ambiguous. I like to look for Dyson spheres, so I'm looking for infrared excesses around stars. There are many, many reasons stars have infrared excesses. Debris disks are a particular confounder. So if I see a star that has too much infrared radiation, I'm not claiming I have found life. I'm not claiming I found a Dyson sphere. I'm very interested in seeing what kind of debris disk it does or doesn't have so that I can follow up with other sorts of observations. But this is also a major problem for biosignatures. If we detect ozone on another planet, there are plenty of abiotic ways we can imagine that could have arisen. And so this is an active area of research in biosignature research as well. How can we get around the problem of ambiguity? Nature is often cleverer than us at figuring out how to do things that seem like they should be from biology. Of course, some technosignatures are absolutely unambiguous. If we find narrowband radio signals or pulsed optical, There is no natural way to generate those. It has to do with Doppler shifts. If you just got enough gas to make enough radio waves, the gas has a temperature, the gas has bulk motion, that means Doppler shifts, that means a width. If it's narrower than that, that has to be engineered. So absolute non-ambiguity is an advantage for some searches for technosignatures. Also, similarly to biosignatures, things like chemical networks that include chlorofluorocarbons are probably pretty ambiguous. If we were to detect such things, I'm sure clever theorists might dream up ways to do it abiotically, but I think it would feel like a real stretch. And the last one is the strength. Which is stronger? Many or most biosignatures are very subtle or weak. What you're looking for is what life has managed to do with the energy it receives from the star. And it's living with its biosphere. And even detecting planets at all is very, very difficult. Detecting the atmosphere is almost impossible right now. We're getting there. Actually finding unambiguous biosignatures as subtle effects in that is extremely challenging. Technosignatures have no limit. Kardashev famously just dreamed up how big they could be. You could use every star in the galaxy to send a radio signal. The point isn't that that's likely. The point is that there's no limit. They could be extremely strong. So again, the tail out to very large values is long. I would argue Earth's technosignatures are already probably more visible than their biosignatures. If you were on Alpha Centauri and you had to prove to someone that there was life orbiting the sun, you've kind of got two obvious ways to do it. You could build LUVOIR, a 10-meter space telescope, image the Earth, try to take a spectrum of it, and say, see methane and ozone. There you go. You could also just use 1970s, 80s technology and build an enormous radio telescope and detect our aircraft radar. It would be easier. The most obvious signature of life on Earth is probably its technosignatures, not its biosignatures. Other numbers for you: a 10 kilowatt laser on a telescope can outshine the sun. A 1 megawatt radar pulse can be detected at Alpha Centauri. The breakthrough starshot laser would be visible across the universe, to give some bigger numbers for you. So for my scorecard, in terms of abundance, technosignatures already win in the solar system, much longer tail to large numbers. In terms of longevity, for the past, biosignatures win by many orders of magnitude. But in the future, we don't know what the value should be, and it's very plausible, again, that technosignatures have an order of magnitude advantage. In terms of detectability, it appears for current Earth life to be about a tie, with maybe an edge for technosignatures. But in the future, as our technology grows, there's no reason it could not be much larger. And in terms of ambiguity, that will plague both kinds of search, but some technosignatures have a clear advantage. So my point is definitely that we should not be looking for biosignatures, that technosignatures is a superior strategy. I think that depends on your priors, and I don't know. These are all just guesses and probabilities and stories. My point is that it is not at all clear that biosignatures are a better route forward. So my closing thought, as we think about how NASA is moving forward, and in particular, there was this report on the Standards of Evidence workshop for the detection of life and how we're going to think about detecting life. I think the SETI and biosignature communities can benefit a lot from talking to each other. We're both struggling with all of these issues of how we estimate detectability, what do we look for, how do we communicate ambiguity, how do we communicate possible detections, how do we set standards for when we think we say this is worth looking at for life before that firm detection. And I think more interaction would benefit both. And in terms of an overall strategy, I think the mixed strategy of pursuing both makes the most sense. Thanks.